Now, what is the reaction mechanism? So, a reaction mechanism is a series of individual chemical steps by which an overall chemical reaction occurs. So, it's a general overview of what is a reaction mechanism. But if we want to go over it deeply, we just have to start by the point that we first understand the rate of reaction and the requirements for an effective reaction to occur. And up to this point, we always had a look at the net or overall reaction. It means that the reactants going to the products. We didn't look at the steps at which that reaction happens. For example, we just looked at NO2 plus carbon CO produces NO plus CO2. We just looked at it. It's the simplest view since many reactions go through a series of steps before the product is formed. For example, if we want to, for example, this equation, NO plus NO2 produces NO3 plus NO, and then this is the first step. The second step is NO3 plus CO produces NO2 plus CO2. The process by which, and again, there is another statement about the reaction mechanism, and it says the process by which a reaction is called the reaction mechanism. It's a simpler way to call it. And each process in the reaction mechanism is referred to elementary step. This one is an elementary step, and this one again is an elementary step, with a number of reactant molecules defining the molecularity of that step. So now let's say that if a reaction have one reactant molecule, we call that reaction a unimolecular. So if we have one reactant molecule, we call it unimolecular. And if we have two reactant molecules, we call it bimolecular. And if we have three or more, we call it termolecular. We get to this point, and we will try to give you more example on what can be a unimolecular, what can be bimolecular, and what can be a termolecular. And now let's complete this reaction. This reaction overall equation would be NO2 plus CO produces NO plus CO. And how did we get that? First, let's say that we have two reactant molecules here, 1 and 2. So this makes this reaction a bimolecular step. And again, in this step, we have 1 and 2 reactant molecule. So overall, there are two elementary steps, and each step is bimolecular. We have 1 elementary step and 2 elementary step, and each step have 2 reactant molecules, so each step is bimolecular. Okay, so now let's get to the main point of this video. Now, NO2 and NO2 cancels each other out, and NO3 will also cancel NO3 on the second reaction. And if you have noticed, NO3 does not appear in the overall reaction as well. We have NO2, but not two of them, as well as NO2. So a species that is involved in an elementary step of a mechanism but does not appear in the overall reaction is called an intermediate. But if we want to be more specified, the reactant that the molecule that consumes first and then produces again is called catalyst. So and the species that is produces first and then consumes is called intermediate. So notice that in this reaction, NO2 consumes first and then produces again. So NO2 here can act, so I'm sorry, this one is an NO2. So notice here, this NO2 acts as an catalyst, and NO3 produces and then consumes. So NO3 is our intermediate. There are three criteria that we have to consider for any mechanism. One is that the elementary step must add up to the overall balance equation. And second, the elementary step must be physically reasonable because it's either unimolecular or bimolecular. The mechanism must correlate with the experimental rate law. This is obvious. And now let's get into the rate laws and elementary steps. If we know the reaction elementary step, then we can predict its rate law from its molecularity. And that's as if, for example, the reaction A plus B produces product, right? This one is an elementary step. If this is an elementary step, the rate law would be K, A, B, right? Let me write it, rate. And the rate law for this elementary step is second order because each has one, and the order of overall reaction would add up. It's like, how do we calculate it? We add their order together, so 1 plus 1, order of A and order of B would be 2, so makes it a second order reaction. And the molecularity would be bimolecular. We have 1 and 2 reactants here. We can only use molecularity to determine the rate law for an elementary step, and this does not apply to an overall reaction. Rate laws are determined experimentally for the overall reaction, and that's just for the elementary steps. So now, as we said, let's get to the example of what can be a unimolecular, bimolecular, or termolecular. If we have, for example, A, and A produces a product, we call this, the molecularity would be 1, and the rate law would be Ka. If we have A plus A product, and if we have A plus B product, we have this bimolecular reaction, or the molecularity would be 2, and the rate law would be Ka, since we have 2, A with the power of 2, A and B would be again Ka, B. And now if we have the third level of molecularity, it would be like this. For example, A plus A plus A produces product, or A plus B, or for example A plus B plus C product. The molecularity level would be 3, 3, 3, but the third level is like, it's a rare thing, so they probably won't give you only examples, but there's always a chance for it. And so the rate law would be Ka with the power 3, Ka B, but notice that we have 2 of A, so K with A would be the power of 2, B, C. That's how we write our rate law. And there are 2 facts that we should consider. One is many reactions occur via a multi-step mechanism, and in any multi-step mechanism, some elementary steps are likely to be faster than the others. And there's a definition called rate determining steps. And the slowest elementary step in a mechanism, the overall reaction rate, the rate law and the rate law is governed by the rate determining step, which is usually the slowest one. So I will give you guys an example for the analogy of the rate determining step. For example, we have a toaster here plus a bread, for example, which produces toast. And then we have a toast and butter, which produces toast butter. So the reaction of like getting a toast bread is slow, and the reaction of getting a toast and butter and until that butter melts on the toast is faster than toasting the bread itself, so faster and slower. And toasting the bread, it's the rate determining step because it is the slowest step in the process. And let's get back to our example. For example, here, NO2 plus CO produces NO plus CO2. What were the process of this reaction? It was NO2 plus NO2 produces NO3 plus NO. That's our first elementary step. Number 1. We had and then that NO3, which acts as our intermediate, plus our CO produces NO2 plus CO2. That's our second elementary step. And if we want to like draw the graph of this reaction, I'll draw it like here to be more visualized. Okay, the reactants are here, and the EA for the energy, for the activation energy would be something like this. I would draw like this. So these are our products here, like that overall reaction. Step 1, which is how. Step 1 have a higher activation energy, means that it's the slowest step. The second one has a lower. This is, for example, EA1, EA2. The second one has a smaller rate constant. Has the lowest activation energy, so it's the faster one. And this first step, since it has the lowest, since it's the lowest step, it determines the overall rate law for the reaction. And from that, we can conclude that step 1 has a smaller rate constant, and step 1 determines the overall rate. Step 1 has higher activation energy. Then there are some things that we should consider in the rate constant for writing a rate constant in a reaction mechanism. The subscript on the rate constant indicates the elementary step involved. K1 is a rate constant for the step 1, and a negative subscript refers to the rate constant for the reverse of an elementary step. For example, K-1 is a rate constant for the reverse of the first elementary step. If we have like multi-step reaction with an initial slow step, it would be something like the first, like the one that we put as an example. This one is slow, so I would put it down. This is our slowest step, and this one is the fastest step. And that will be our overall reaction. NO2 plus CO produces NO plus CO2. For the multi-step reaction with an initial slowest step, like here, the overall rate for the reaction is the rate of the rate determining reaction, which is our first step. So the rate would be K1. Notice here. And here we have K1 and we have K2. That's what I'm trying to show. that's the rate of reaction would be for the slowest step. Like we choose the slowest step rate for the overall rate law. And there's another fact that we should consider, that the next part would be NO2 concentration, and since we have two of them, NO2 with the power of 2. And then if we have this condition is for the multi-step reaction with an initial slow step. And then if we have a multi-step reaction however, here we have with an initial fast step, the thing would be different. Fast step. So, for example, let's consider this equation. NO2, that's a reverse, NO, that's a reverse reaction, N2O2, our first elementary step, and it's fast reversible. For the second elementary reaction, we have N2O2 plus H2 produces with the K2. Okay, wait. Okay, now let's hear it. This is our K1. So this one, as we said, the reverse of that reaction would be K -1. The K2 rate produces N2O plus H2O. For our third elementary step, we have N2O plus H2 with the K3 rate. We reduce N2 plus H2O. So here, this one is our fast step. This one is our slow step. We said the slow step is rate determinant. Notice that, like, we do not call this a termolecular, because if we have 3 elementary steps, it does not determine that that we have a termolecular or like bimolecular. It depends on the number of reactants that we have. In this case, this one is unimolecular, this one is bimolecular, and again this one is bimolecular, and we have 3 elementary steps here. And now the overall reaction of this would be, we cannot see N2O2 here, and we have 2NO plus 2H2 produces N2 plus N2 plus 2H2O. So now, how can we determine the rate law? If we want to consider like the expected rate law for us would be, let me write it as expected rate law. It would be K, we use the slowest step, it would be K2 and N2O2 H2, but that's our expected. But the problem here, N2O2 is an intermediate, like the one that the thing that we cancel. So it used up in the next step, which is here. And I'm sorry for like covering this again. I meant this one. So I'd use up in the next step, and the rate law must be expressed in the terms of the actual reactants. So see, if we want to write a rate law like this and use this slowest step reaction, we get to have N2O2 in our rate law, which we don't because it's an intermediate, and we do not use intermediate in our rate law. We use the actual reactants. And so we go like try to solve the problem. First step, it's reversible. So rate of forward equals to the rate of reverse. So what it means is that we have, no, we don't have any coefficients. Yeah, we do have any coefficients. We have two coefficients. So we have 2NO reverse reaction N2O2. We have K1 and negative K1 negative K negative 1. So what it means is that the rate of producing N2O2 in the first step is equal to the rate of consuming N2O2 that produces NO. So how do we write it? We say K1 NO with the power of 2, the coefficient here, equals to the K negative 1 N2O2. The rate would be, for the N2O2 would be K1 over K negative 1 times NO with the power of 2. So the slowest step rate would be the thing that we wrote. Rate of slow step was K2 N2 O2 H2. And now instead of N2, we found that N2 is equal to K1 over K negative 1 times to N2 NO with the power of 2. We try to put this equation here instead of N2O2. So the rate law, the actual rate law, would be K2 K1, notice that we try to write this equation here, K negative 1 NO 2 times H2. We just changed the formation on how do we write the N2O2 to this form. And now let's get to an example and try to solve it. Please pause the video and try to check your understanding of the concept. Sometimes they can be confusing, so it's a good way to test it. It says the following reaction has a second order rate law. The reaction is H2 plus 2 iodine chloride produces iodide plus HCl, 2HCl actually, 2HCl, and the rate law is KH2 ICl. I want you guys to propose a possible reaction mechanism for this reaction. Sometimes you have to look what you have, and sometimes you don't have the intermediate. You can get it. To simplify it, I can give you the intermediate, but I want you guys to think about it. How can you find the intermediate here? Okay, so now we're going to start. First, we have to find the slow step and the fast step. Because the slow step, it's the rate law determining, and we can we can guess it if the first step is the slowest step or the fastest step. When you don't have any information of it, you can probably sometimes guess that the first one is the slowest step, but we want to like be sure about it. So let's say the red law is H2 plus iodine chloride. And what do we have here for the net overall reaction? H2 plus 2 iodine chloride. So we can guess, we can be more sure that our first reaction elementary step is the slowest step. So we write it H2 plus iodine chloride with a K1 rate produces something plus HCl. And because we have HCl here. And for our second step, we have that intermediate that's going to be consumed, plus we have ICl here, and that intermediate, it doesn't matter, I just want to like ICl here, I just want to like be more precise. Then we have organized element. We have K2, we have iodide plus, and again HCl. So we have 2 iodine chloride here, plus we have H2 in our overall reaction, and we have 2 HCl plus iodine. So now, how are we supposed to find the intermediate? So we can just use this first one. So again, let me show that this is our slow step. So now, let's see. We have H2. We have 2H here. We have 1 iodine here. 1 iodine. And we have 1 chloride. We have 1 chloride here. And we have 1 hydrogen here. So now, what are we missing? We miss 1 hydrogen and 1 iodide. What do we have to do? We say the intermediate would be hydrogen HI. And again, here we have HI. So notice that these cancel each other out. So HI is our intermediate here, which is a great way to find. Sometimes they would give you the intermediate, and sometimes you just have to find it, which is an easy way to like what I said. You can just find the step that you're doing, find which one is the slow one, and then you can easily try to find that intermediate. And HI is basically the molecular form in the first collide, so with a iodine chloride molecule to form another HCl and I2 iodide molecule. So that's how we just simply try to like reasoning and what's happening. And then you guys for watching the video. I hope you enjoyed it and learned something from it. Please like and subscribe, and if you have any further question, you can ask me on the comments. I would definitely answer that. Thanks.